Okay, so before starting the lecture, let me briefly introduce the speaker today, Professor Ahmed Abbes. So he's chargé de recherche, so research director of CNRS French Center of Research of Sciences, and working at IHES. So he's a permanent visitor here, so he made a long visit and he gave even courses 3 times here.
Yeah. Maybe 2 times.
2 times, yes. Yeah. Yeah, and this time he visited for 1 month to work with Tsuji Sensei. And he's planning to coming back next March for another 3 months visit at this French laboratory here. Yeah. So today he will going to tell us his recent work on the P-adic Simpson correspondence. So please start.
Thank you very much. So thank you, Takeshi, for the introduction. I would like to thank Atsushi for giving me the opportunity to speak here, and to thank Takeshi Tsuji for the invitation to stay here for 1 month, and the 2 Takeshis for the hospitality. It's always a great pleasure to be here, and it's a great honor to speak in this colloquium. So the topic I will speak on today was initiated by Faltings in 2005. Before I say what it is about, I would like to say a few words about its origins. It has mainly 2 origins, one complex and one P-adic. So the complex origin gives it its name, namely this complex Simpson correspondence was a model for the P-adic Simpson correspondence. And it shares with this complex origin the formalism. And the other origin is P-adic, it's Sen theory. And Sen theory shares with the P-adic Simpson correspondence the main goal, which is to describe the P-adic representations of étale fundamental groups of algebraic varieties over P-adic local fields. And it also shares, and this is maybe the key point, the techniques which are coming from P-adic Hodge theory. So I will start first by saying a few words about the complex origin. I'm not expert in complex analysis. The story started in 1965, where Narasimhan and Seshadri established an important bijection between bijective correspondence between the set of equivalence classes of irreducible unitary representations of the fundamental group of a compact Riemann surface X, and the set of isomorphism classes of stable holomorphic vector bundles of degree 0 on the curve. And the correspondence is constructed, very easy to describe. Starting from a unitary representation rho of pi, we associate a vector bundle, a holomorphic vector bundle, which is defined as a twisted product of the universal cover, x tilde of x, by C to the R, and this twisted pullback is a quotient of the usual pullback by the diagonal action of the fundamental group. So then this correspondence was extended to in higher dimensions, first of all by Donaldson for smooth projective varieties, and by Uhlenbeck and Yao for Kähler manifolds. The next step came much later in the 80s, where Simpson extended this correspondence to general representations of, let's say, of the fundamental group of a smooth projective variety X. So we went from unitary representations to representations, general representations of the fundamental group. But to do this, we need an extra data on the holomorphic bundle, namely the notion of Higgs field. And this notion was first introduced by Hitchim for curves. So let me say what it is. So we'll say a Higgs bundle on our smooth projective variety X is a pair E theta, where E is a holomorphic or here equivalently an algebraic vector bundle over X. And theta is a linear, OX linear morphism from E to omega 1x tans over OXE. This omega 1x is the sheaf of smooth one differential forms on X. And this linear morphism is required to satisfy an integrability condition, which is theta wedge theta equals 0. So it looks a little bit similar to a connection, except that it's linear instead of satisfying Leibniz rule. And this correspondence satisfies several interesting features that we will see either are already established or serves as a motivation in the P-adic context. So the first property has already an analog in the P-adic context. Namely, if we start with a representation of the fundamental group, or equivalently from a local system L on X, and take the associated Higgs bundle E theta, we can then form the Dolbeault complex, omega dot x tans OXE. So this is the OX linear complex, which is built from omega. Then we have a canonical isomorphism between the cohomology of L and the hypercohomology of the Dolbeault complex. Okay? So, as I said, this is already established in the P-adic context. The second feature, which is probably the most advanced result in this area, established by Simpson, is not known yet for the P-adic correspondence and serves as a motivation. Sometimes people believe it, sometimes people don't believe it. So namely, Simpson established that this correspondence is in fact induce an equivalence of categories between the category of linear representations of pi and the category of semi-stable Higgs bundles on X with vanishing Chern classes. Okay, so I will not say much more about this, except that, in fact, this correspondence is not as explicit as the Seshadri-Narasimhan's correspondence. So Simpson constructed it using harmonic bundles. And these, at this point, the two theories bifurcate, namely the P-adic and the complex theory. So I will shift to the second origin, namely the P-adic origin of the P-adic Simpson correspondence, which is Sen theory, that in some sense give us more the techniques we will use. So Sen theory is devoted to the study of P-adic representations of a P-adic Galois group. So the setting is the following. K will be a complete discrete valuation field of characteristic 0 with perfect residue field of characteristic P. I will fix a separable closure K bar of K and denote by G the Galois group of K bar over K. By OK the valuation ring of K. And OK bar will be the integral closure of OK in K bar. And I will denote by C the P-adic completion of K bar. So Sen theory proceed by a kind of dévissage in some sense to study the Galois representations of G. And for this I need some notation, so I need to introduce two fields. So first of all, I need the cyclotomic character, so I call it chi. So this is a character of G with value in Zp star. And it's the character that describes the action of G on the P power roots of unity in K bar. Okay. I also need the P-adic logarithm. So this is a homomorphism from Zp star to Zp, which is given by the usual expansion when x is close from 1, which means x minus 1 is in Pz, and which is extended to all units here by requesting the following formula. Log of x is equal to log of x to the power p minus 1 divided by p minus 1. So we can take the composition, the log of the cyclotomic character. We get a continuous homomorphism from G to Zp. And I will denote by H its kernel, and by gamma its image, or equivalently the quotient of G modulo H. So this is a profinite group isomorphic to Zp. And I will introduce the fields which are fixed by the group H. I call it K infinity, the Zp cyclotomic tower in some sense. And I will denote by L its p-adic completion. So this is the closure of K infinity in C, which is the p-adic completion of K bar. Even if we are interested in the study of just QP linear representations of G, in p-adic Hodge theory, we need to extend the base field to bigger period fields or period rings. And in this context, the first important period field is C itself. So we need to study not just linear representations, but semi-linear representations. And Sen theory is concerned with C representations of G. By this, I mean finite dimensional C vector spaces equipped with a continuous semi-linear representation of G. I will denote this category by rep CG. And we can introduce similarly the category of L representations of gamma. I denoted by rep L gamma. And K infinity representations of gamma. Okay? So all these are semi-linear continuous representations on finite dimensional vector spaces over either C, L, or K infinity. The first important result due to Sen and Tate build on fundamental results of Tate about the Galois cohomology of G with values in twist of C or K bar or K infinity is the fact that by base change we have equivalences of categories between the category of K infinity representations of gamma and the category of L representations of gamma. So here we just extend scalars from K infinity to L. And from the category of L representations of gamma to C representations of G by extending scalars from L to C. So these base changes induce equivalences of categories, two equivalences of categories. And Sen even, in fact, constructed explicitly quasi-inverses to these explicit quasi-inverses of these equivalences of categories. So if we are interested in a given C representation of G, we find ourselves with a K infinity representation of gamma that we have to study. And for this, we have the next theorem of Sen that you should see as a kind of p-adic analog of the L-adic monodromy theorem of Grothendieck, which says the following. For every K infinity representation V of gamma, there exists a unique K infinity endomorphism sigma of V satisfying the following property. For every X in V, there exists an open subgroup gamma X in gamma such that for every element gamma in this subgroup gamma X, the action of gamma on X is given by the exponential of log of the cyclotomic character applied to gamma times sigma applied to X. So this sigma is in some sense a kind of p-adic normalized p-adic logarithm of the monodromy. So this endomorphism is called Sen endomorphism. It has a lot of important properties. First of all, its characteristic polynomial has coefficients in K. And in fact, it determines the isomorphism class of V itself. More precisely, we can formulate the statement like this. So if we denote by S K infinity the category of finite dimensional K infinity vector spaces equipped with a K infinity endomorphism, so it's a pair, vector space plus an endomorphism, then we constructed, with these two theorems of Sen, a functor from the category of C representations of G to the category S K infinity, first of all by descent to K infinity representations of gamma, then by associating to the representation the pair formed by V and its Sen endomorphism. Okay, so it's a functor, and this functor is in fact exact and faithful. And moreover, the pair V sigma determines completely W up to an isomorphism. Okay, so this is in fact the first instance of p-adic Simpson correspondence. This sigma is, in a certain sense, a Higgs field. Okay, it's an arithmetic Simpson correspondence in some sense. So what is precisely the P-adic Simpson correspondence that was initiated, as I said, by Faltings in 2005? So let me fix the setting. First of all, I will denote by S the spectrum of OK. Eta is generic point. S bar spectrum of OK bar. Eta bar will be its generic point. And curly S will be the formal spectrum of OC. And I will fix a smooth S scheme X and denote by curly X the P-adic completion of the base change of X from S to S bar that I will denote by X bar. Our goal is to construct a functor from the category of QP local systems over X eta bar for the étale topology to the category of Higgs bundles over OX1 over P. Okay, so this category is clear what it means. So it's P-adic representations of the étale fundamental group. Let me describe a little bit what is this category. So this category here is the category of pairs, okay, formed by a locally projective OX1 over P module of finite type. So it's a module over the formal scheme, but where P is inverted, equipped with a linear OX linear morphism from M to M tans OX omega 1 X over S, which satisfies the usual integrability condition theta wedge theta equals 0. And what do we request from this functor? Mainly that it's compatible with natural cohomologies. That is, if X is proper over S, we would like that for every, I put here, admissible QP local system L, I will say what it means, this admissibility condition later, there is a canonical isomorphism between the étale cohomology of L, where I extend scalars from QP to C, with the hypercohomology of the Dolbeault complex of the Higgs bundle associated to L. So this Dolbeault complex is constructed as in the complex case from theta. Okay? And this isomorphism, in fact, should generalize in a certain sense the Hodge-Tate decomposition. Like the isomorphism I described in the beginning was a generalization of Hodge theory. So let me remind you the following statement, which is the Hodge-Tate decomposition. For every proper and smooth variety x over k, and for every integer n, there exists a canonical functorial GK equivariant decomposition of Hn xk bar qp, where we extend scalars from qp to c, with the sum of the Hodge cohomology, so from I from 0 to n, hi xc omega n minus I xc over c, twisted by I minus n. So this fundamental theorem was proved by Faltings, Tsuji, and NISSAY. So how this how this isomorphism could generalize in a certain sense this decomposition? So we expect that when we take the constant sheaf QP, the Higgs bundle should be trivial, which means OX1 over P equipped with the zero Higgs field. Then this Durham cohomology will just, this Dolbeault complex will have zero differentials, and we will get just this cohomology here. And in fact, we should think of this functor H as a kind of categorification of the Hodge-Tate spectral sequence, or the Hodge-Tate decomposition in this context, and even of the relative version. Okay, so this is what we want, and how we will achieve that. So the construction is not simple, but there is a kind of very simple, basic cornerstone construction given by Faltings from the beginning that has a lot of defects, and I will first introduce it and then explain its defects and how we overcome them. So it's called, so the context is the following. We take an affine scheme, spec of R, and we assume that it's equipped with an étale map to GM of S, so to a torus over S, GM SD, okay? So we say that this scheme is small because of this étale map, okay? We assume that the spatial fiber is not empty, and for simplicity, we assume that the geometric generic fiber is connected we fix a geometric generic point x bar of the geometric generic fiber and denote by delta the geometric fundamental group pointed by x bar. Then these TIs here induce in the ring R elements that we will call TI. And we start by choosing towers of Pn roots of these TIs in the field of rationality of the geometric generic point. Okay? So in this way, we can define a quotient of the fundamental group, delta infinity, which is isomorphic to Zp of 1 to the power d. So we have here a surjective homomorphism given by characters chi1, chi-d. And these characters just describe the action of delta on these towers of Pnth roots of TIs. Okay, so this is the first important information. The second notation I need is that I have the ring R. I need to extend it to OK bar. I will denote this by R1, and I will denote by R1 hat its p-adic completion. Usually hats will denote p-adic completion in this lecture. Let me now describe the simplest construction of the p-adic Simpson correspondence. We start with a free R1 hat module of finite type, equipped with a continuous p-adic representation delta phi of delta infinity here. Okay? So this representation is really linear because delta infinity does not act on this ring here. And we assume that this representation is in fact a trivial modulo p alpha for a certain rational number alpha bigger than 1 over p minus 1. Then we can form the logarithm of phi because delta infinity is abelian and because of this smallness condition on the representation. Okay, it's trivial modulo this. So we can form log of phi, and log of phi, we can write it as a sum from 1 to d of endomorphisms of m, theta i, tensor the characters chi I, then we have to kill the twist here, so we multiply by xi minus 1, where xi is just a zp basis of zp of 1. So these theta i's here, because delta infinity is abelian, are just endomorphisms of m that commute with each other. Okay? In fact, they are also small because the representation is small. Okay, then what we can do is the following. We can just change this character, chi I, into d log ti. So just a formal substitution up to now. So we get a morphism, an R1 hat linear morphism, from m to m tans omega 1 r over OK twisted by minus 1, coming from this xi, which is the sum of theta I tensor d log ti tensor xi minus 1. And because of this commutation of the theta i's, it's a Higgs field, namely it satisfies theta wedge theta equals 0. So this is, as I said, the basic construction. But this construction, in some sense, has some defects. I'm not interested in just delta infinity representations. I'm interested in representations of delta, which is a bigger group. Delta infinity was just a quotient. This is the first point. And the second point, as in the complex, as in Sen theory, I am interested in representations with more general coefficients. So first of all, what is the coefficients I would like to consider? The analog of OC in some sense, or of OK bar in this case. So this is denoted by R bar. It's a subring of K bar of X bar, which is the maximal integral extension of R, which is unramified over the generic fiber. Okay, it's really the analog of OK bar. And then I am interested in the category of continuous p-adic semi-linear representations of delta, the geometric fundamental group, on R bar hat modules. I call these representations generalized representations, and I denote their category by rep R bar hat of delta. Inside this category, I am interested in a smaller category, namely the category of smaller representations, namely the full subcategory of representations, m phi, such that m is a free R bar hat module of finite type, which has a basis made of delta invariants modulo p to the alpha elements. It means I can find a basis which is delta invariant modulo p to the alpha, where alpha is a rational number bigger than 1 over p minus 1. Okay. And I can define in a similar way the small representations over R1 hat of the group delta infinity. This is from the Galois side. On the Higgs module side, I will consider small Higgs modules and denote their category by HM small R1 hat. So this is the category of pairs M theta, where M is a free of finite type over R1 hat. And theta is an R1 hat linear map from M to M times omega 1 R over OK twisted by -1, which satisfy the integrability condition and which vanish modulo P to the alpha for a certain alpha bigger than 1 over P minus 1. Then the fundamental result of Faltings, which replaces this descent results of Sen, says that in fact the base change from small R1 hat representations of delta infinity to small R bar hat representations of delta, which consists just in extending the coefficients from R1 hat to R bar hat, is in fact an equivalence of categories. So it's a descent result for small representations. So like this, now we are able to construct our functor for R bar hat representations of delta. First of all, we already constructed here a functor from small R1 hat representation of delta infinity to small Higgs bundles. And I did not say it at the time, but this was in fact an equivalence of category because we have the exponential that will give the inverse, okay? And here we have an equivalence of categories from small R1 hat representation of delta infinity to small R bar hat representation of delta. So we just choose a quasi-inverse of this functor and compose the two. We get a functor like this, which is the P-adic Simpson correspondence. Several problems arise from this construction. The first serious problem is that it depends on the choice of the TIs. And this will not allow us to glue it. The second problem is that, in fact, we are interested not in integral representations, but rational representations, means when we invert P. And Faltings, in fact, claimed that he can extend this construction for rational coefficients, which is not obvious. In fact, it requires a very subtle descent for small representations with rational coefficients, which was established only later by Takeshi Tsuji. Okay, so Faltings explained in a very short paper, sketch a project which aimed to globalize the construction for small generalized representations by using deformation theory. And then he proposed to extend it to all generalized representation by descent. And since 2005, there were a lot of works aiming to achieve this project. So I list here some results. So I developed with Michel Groux an approach to study the first point, namely the construction for small generalized representations by a correspondence à la Fontaine, which uses a period ring that we call the Higgs-Tate algebra, obtained from a torsor of lifting, which was inspired by a similar construction in characteristic P due to August Vologodsky. Takeshi Tsuji proposed also a correspondence à la Fontaine between small generalized representations and small Higgs crystals, and he used another period ring, which is built from Higgs envelopes. The two constructions are related. More recently, Hoyer and Xu proposed another approach using hitching fibration that allows to treat more general representations, at least for curves. So this is for the construction. And for the properties, I would like to mention two works about the functoriality of this construction. So first of all, maybe 2 or 3 years ago, with Michel Groux, we studied the functoriality by proper direct image. And our results were conditioned by the existence of a certain lifting. Then in a more recent work, which is in progress with Michel, Groux, and Takeshi Tsuji, we succeeded to remove this dependence on the lifting. And in fact, we propose in maybe the best framework to study the functoriality of the P-adic Simpson correspondence, both by direct image and pullback, based on a new twisting approach of Higgs bundles, Higgs modules, which is maybe the topic of what I would like now to discuss in the second half of my lecture. Okay, so let me give a brief overview of this work with Michel and Takeshi. As I said, the key construction is a twisting functor for Higgs modules. It's a very general construction in a general setup, which turns out to have several interesting applications, including a new definition of the P-adic Simpson correspondence, but also the functoriality of the P-adic Simpson correspondence. So the setup is the following. So I will fix X a topos, and I will equip it with a ring, which is a P-adic ring, which is flat over OC. So it's an OC algebra, flat OC algebra, which is P-adic in the sense that it's isomorphic to the projective limit of OX mod P to the N OX. And I give myself an extension F of a locally free OX module of finite type E by OX. If you don't like topos, you can think here of just a formal scheme, which is locally of finite presentation over OC. It will already cover a big part of the applications. But we need this level of generality for the application to the P-adic Simpson correspondence. Our main goal is to study the category of Higgs OX modules with coefficients in E, by which I mean the category of pairs n theta, where n is an OX module, and theta is an OX linear map from n to E times OX n, which satisfies the usual integrability condition theta which theta equals 0. So what will we do with this extension? We will associate to it first an OX algebra that we call the Higgs-Tate algebra. It's the inductive limit of sim n OX f. I will explain the meaning of this algebra. And from this algebra, we will derive an undo functor that we call twisting functor and denote by tau on the category of Higgs OX modules with coefficients in E. I will give the definitions in a few minutes, but before I would like to say what we do with this functor. We derive three applications. First of all, we define twisted pullback and twisted push forward for Higgs modules. The twisted pullback appeared already in Faltings' original paper in 2005, but the twisted push forward is new. It's a kind of twisted Dolbeault cohomology, and it's a generalization of the analog of the Katz-Oda construction of the Gauss-Manin connection. Okay? The second application is in fact a new construction of the P-adic Simpson correspondence for small Higgs bundles. And this construction in fact encompasses my earlier approach with Michel Gros, and it's not a surprise because in fact the functor tau was inspired by our approach. And the third application is the functoriality properties of the P-adic Simpson correspondence for small Higgs bundles, as I said before, both by pullback and by proper push forward. And in fact, we derive this compatibility property, we derive these functoriality properties from the compatibility properties of the twisting functor. So more precisely, if we have two composable twisting functor, we would like to identify the composition with a single twisting functor. And this requires to give a composition homomorphism for the associated Higgs-Tate algebra. And we will construct a natural one in the context of the P-adic Simpson correspondence, and this is give us the required functoriality. So let me start by explaining the twisting. So we start from our extension f of E by OX, and we associate to it the algebra C, which is the inductive limit of sim n OX f. The transition morphisms here are defined by mapping a symmetric product x1 xn to 1 times x1 xn, and the one is coming from here. I see it in F. So this algebra is in fact just a twisted form of the symmetric algebra of E. If the extension was a split, any splitting identify as C with sim of E. Okay, so then its module of differentials over OX is naturally the pullback of E, and I will denote by D the universal OX derivation, so it's a map from C to E times OXC. And it's easy to see that, in fact, it's a Higgs field in the sense that d wedge d equals 0. Then from this algebra and this derivation, I can define a functor, an undo functor on the category of Higgs OX module with coefficients in E. In the following way, I will map n theta to the following Higgs module that I will define term by term. So first of all, C dagger. C dagger is in fact a weak p-adic completion of C. So it's a generalization of the weak p-adic completion of the symmetric algebra of E. Here we need this weak completion because we need a Poincaré lemma. We are in mixed characteristic 0p, so we need a weak p-adic completion. Then the derivation D induces a derivation on C dagger that we will denote by delta. It's a map from C dagger to E tans OX C dagger. And this derivation is also a Higgs field. On the tensor product n tans OX C dagger, I will take the total Higgs field, namely theta tans 1 plus 1 tans delta. It's not just a Higgs field on this module, it's what we call a delta connection, in the sense that it satisfies a modified Leibniz rule where the universal derivation is replaced by delta. Then I will take for module here just the kernel of the total Higgs field. Total Higgs field equals 0. And I equip it with a Higgs field that I denote by theta tau, which is the Higgs field induced by theta tans 1. So this is an easy fact. Theta tans 1 acting here as a Higgs field on n tans OX C dagger induces, in fact, a Higgs field on the kernel of the total Higgs field. Okay, so this is the definition of our twisting functor. It's in general very complicated to compute this functor explicitly, but if we assume that the Higgs field is admissible, and here come the admissibility conditions I mentioned in the beginning, then the twisting is very easy to compute. So what is this twisting property? Admissibility property. We call it here weak twistability. So we say that the Higgs OX 1 over P module n theta with coefficients in E is weakly twistable by the extension F if the canonical C dagger linear morphism from C dagger tans OX tau underline n theta to C dagger tans OX n is an isomorphism. So first of all, let me remind you that this tau underline of n theta is just the kernel of the total Higgs field acting on this tensor product. So this tau underline is naturally sub OX module of this tensor product. And we extend this inclusion by linearity to C dagger. And we ask that this map is an isomorphism. For these objects, the twisting functor is very easy to compute. Namely, so let n theta be a Higgs OX 1 over P module with coefficients in E. And let me set H to be the symmetric algebra of E dagger. So to give a Higgs field theta on n is the same thing as to give a homomorphism from H, sim E dagger, to the endomorphism ring of n. And because I invert P here, I am allowed to invert P here. So I will denote by mu the homomorphism from H1 over P to ent OXN, which is defined by theta. And I will fix a quotient of this algebra through which this homomorphism factors, any quotient. So I call it B. Because B is a quotient of H1 over P, it naturally has a Higgs field according to the dictionary I just explained before. And I call this Higgs field theta B, and I call it the canonical Higgs field on B. Okay? I make an assumption here. I assume that the Higgs fields, the Higgs OX1 over P modules, n theta and B theta B are weakly twistable in this sense. Okay? Then the conclusion is that, first of all, the B module LB, which is the twisting of B theta B, is invertible, and we have a canonical B linear isomorphism from n tans B LB with the twisting of n theta. So let me explain a little bit here why these are B modules. So tau of, maybe I explain it here first, tau of n theta is naturally a Higgs module. So it has a Higgs field, and as a Higgs field, it became automatically H1 over P module. And because N is a B module, in some sense the action of H1 over P factor through B, the action of H1 over P on tau of n theta also factors through B. So this one is naturally a B module. This one also, so I call it LB. So the statement says that this B module is invertible. LB is an invertible B module. And this B module, tau of n theta, is isomorphic just to the twist. This is the name. N tensor over B LB. Okay? Okay, so this is nice, but you may wonder how we check this twistability condition. Maybe it's too complicated. In fact, we have a much simpler condition to check, which implies it, namely smallness. And this is will make the connection with Faltings. So I will consider here Higgs module over the formal scheme. So let X be a C formal scheme, which is locally of finite presentation. An S formal scheme, which is locally finite presentation. And here S is the spectrum of OC. And I will consider for X the topos just the Zariski topos of the formal scheme. But for the ring OX, I will allow a little bit of flexibility. So it's an OX algebra, an O curly X algebra. I assume just that the module E descends to O curly X. So there is a locally free O curly X module omega of finite type such that the pullback is exactly E. Then I can speak about smallness on the formal scheme. So a Higgs OX module curly n theta with coefficients in omega is epsilon small for an epsilon which is a rational number strictly bigger than 0 if the image of n by theta is contained in P epsilon omega times OX n. So in some sense, if the Higgs field vanish modulo P epsilon. And I will say that it's a small if it's epsilon prime small for a rational number epsilon prime bigger than 1 over P minus 1. And this 1 over P minus 1 is related to the P-adic exponential and logarithm. And I will say that an OX 1 over P module n theta is CL small, CL for coherent lattice, if n admits a coherent OX1 over P lattice curly n, which is stable under theta, such that curly n theta is a small in this sense. And I will say that it's locally CL small if this property holds Zariski locally. Then we have the following proposition, which says that let n theta be Higgs OX1 over P module with coefficients in omega, and let H be the symmetric algebra of omega, a dual, and let A mu be the homomorphism from H1 over P to ONT OXN defined by theta. And let me take now for B exactly the image, not any quotient through which the action factors, and denote by theta B its canonical Higgs field. Then we have the two properties. If n theta is locally CL small, then the pullback or base change of n theta over OX is weakly twistable. And the second property, if n theta is CL small, then B theta B is CL small. So this means that our admissibility condition include, in fact, absorb the smallness condition of Faltings. Okay, so this is all I want to say about this twisting functor, which is really very simple. And I would like now to discuss the application of this twisting functor, starting by explaining to which extensions I will apply it. The extensions to which I will apply this twisting functor are obtained from deformation theory. And I will explain this construction of extensions in a very simplified, abstract context to avoid the technical details. So my context will be the following. So I have a commutative diagram of schemes where the horizontal lines are first order thickening, so they are closed immersion defined by ideal of square 0. Down B to B tilde is defined by an ideal IB, which is an OB module, and I assume that this ideal is invertible, okay, as an OB module. I assume that F tilde is a smooth, and this square is Cartesian. I do not give here any map, it will appear later, but I assume that the exterior rectangle is Cartesian. And moreover, I assume upstairs, because I do not assume anything on G tilde. Upstairs, it's defined also by an ideal IY, which is an invertible OI module. So automatically, IY will be the pullback of IB. Then I consider precisely the set of all maps that fill this diagram in such a way that it remains commutative. Namely, I consider Ly tilde over X tilde the torsor of liftings of H to a morphism from Y tilde to X tilde. Okay? It's a torsor in the étale topology of Y. Okay? It's defined here. And it's a torsor under the OI module, hom OI, of the pullback of the differentials, omega 1 X over B. So I pull back the differentials here to the ideal IY. Okay? And like for any torsor over an OI module, I can speak about the notion of affine functions. So I will take here, denote Fy tilde over X tilde, the OI module of affine functions on this torsor. So it's an extension of a module E, which is just the pullback of the twisted differentials omega 1 X over B twisted by EB minus 1 by OI. So it's really an extension like the extension I considered in the beginning. And in fact, what is this extension? Its class is just the abstraction of lifting this map to a map here. So I constructed explicitly an extension that realized this abstraction. Then a very easy computation shows that the torsor L is represented by the spectrum of the Higgs-Tate algebra associated to this extension. Okay, so this is the usual yoga between torsors and Higgs-Tate algebras. Okay, fine. Before I explain the application of twisting by this extension, I would like to discuss a little bit the functoriality of this construction. So I take my diagram and I insert another level here. So I add a first order thickening in the middle, x prime to x prime tilde. I assume that this map is also smooth and that this rectangle is Cartesian. Then what I can do is that I can compose lifting. So if I have a lifting here, the composition will be a lifting here. Okay? In terms of torsors, it means that I have a morphism from this torsor cross the affine pullback of the torsor L x prime tilde over x tilde. I will say what means this affine pullback to the torsor of liftings of y tilde over x tilde. So by affine pullback, I mean, first of all, I do the pullback. I get a torsor under h prime minus 1 module, and I enlarge this module by extension of scalars to an OI module and enlarge the associated torsor. So this is just easy construction. So I get a morphism like this, and it's easy to see that this morphism can be converted to a homomorphism of algebras, of Higgs-Tate algebras, phi, from the Higgs-Tate algebra of y tilde over x tilde to the pullback of the Higgs-Tate algebra of x prime tilde over x tilde, tensor the Higgs-Tate algebra of y tilde over x prime tilde. So we call this homomorphism the composition morphism of Higgs-Tate algebras. And this is in fact the key tool for the study of the functoriality of the P-adic Simpson correspondence. And why? Because this homomorphism gives us an isomorphism between the twisting functor of y tilde over x prime tilde over x tilde with the composition of the twisting functors of x prime tilde over x tilde and y tilde over x prime tilde. This just for weakly twistable Higgs modules, because we cannot compute these twisting functors in general. So if this is really the property that will be converted into functoriality of the P-adic Simpson correspondence. At least for pullback, it's just this. For direct image, you need to combine it with cohomological study of the map. Okay. But before, let me explain why the twisting functor is, in a certain sense, connected with the P-adic Simpson correspondence. Like it looks very far as a construction. And for this, I will go back to my diagram here. I assume I am given a group G that acts on Y and Y tilde in such a way that this closed immersion is equivariant, and I will act trivially down, and all maps are equivariant. Okay? So this is my new setting. So I add a group acting on Y and Y tilde. Then my extension F and the associated Higgs-Tate algebra C will naturally become G equivariant OI modules, okay? And with this, I can in fact enrich the twisting functor into a functor in the category of G equivariant Higgs modules. So I start first of all by Higgs module over OX. So it's an OX module, an OX Higgs module with coefficients in E. I pull it back to Y, so it acquires naturally a G action, and then I twist it there by the extension F. I get, first of all, a Higgs module over OI with coefficients in the pullback of E, but which is naturally equipped with an action of G. So it's an equivariant Higgs module. So in fact, this functor, if I forget the Higgs field, is exactly the P-adic Simpson correspondence. For this, I need to choose carefully the thickening iota. So I will explain this thickening a little bit later, but just after. But let me mention before going, because I will not have time to explain the other applications, the important byproduct of the way of seeing the P-adic Simpson correspondence in this way. First of all, as you can see here, we don't get just an action of G on this OI module, but we get naturally a Higgs field. And in fact, we obtain a canonical Higgs field on every small generalized representation. In this context, it means a small G equivariant OI module. And in fact, this canonical Higgs field is a generalization of the P curvature of an integrable connection. The second important application, and this was our goal, and this is what takes a lot of work, is that we obtain from the compatibility of the twisting functors via the composition morphism of Higgs-Tate algebra phi, functoriality properties of the P-adic Simpson correspondence. Okay, so in the 7 minutes that remains, I would like now to tell you, go back to the example I started from, which is small schemes, and explain in this context how this new construction works. So just in that affine case. So X is again small affine scheme over S, which is spectrum of OK. I remind you that this means that it's étale over an S torus. I fix a geometric generic point X bar of X eta bar. And I will denote by delta as before, geometric fundamental group, and R1 bis change of R to OC. And I consider this diagram. So I apply my previous constructions to this situation. So here we have first order thickening. So let me start from down. So it's a thickening of spectrum of OC, which is Fontaine universal P-adic first order thickening. So for the expert, this is defined by the homomorphism of Fontaine, which is called theta, from the ring of Witt vectors of OK bar flat to OC. So this is a homomorphism that gives rise to all period rings in P-adic Hodge theory. So we take that homomorphism. We know that its kernel is generated by a non-zero divisor that we denote usually by psi. So, and we take its first order thickening. So the condition that the ideal is OC invertible is implied by this condition. Then upstairs, what we do, so we do the same construction a la Fontaine here by applying it to R bar. Okay, R bar was the maximal integral extension of R, which is unramified over the generic fiber. Okay, and again here we have a theta homomorphism, which kernel is generated by psi. So this exterior diagram is Cartesian. But we have nothing natural here over R1. Okay, no natural thickening of R1, so we choose one. So we are in an affine situation, so the morphism is affine here, so there is no abstraction to lift, but we have to choose. And the construction will depend on this choice. And when we will globalize it, there will be an abstraction, so it means this is the complication of the P-adic Simpson correspondence, that we have always to choose a thickening like this. Okay, once this thickening is chosen, we can define in this diagram the torsor of liftings here. So call it L x mat tilde over x tilde. It has an extension, it defines an extension of affine functions. I call it curly f. It's an extension of a certain module of differentials by r bar hat, where the module of differentials is the module of differentials of omega 1 r over OK, where I extend twisted by psi minus 1, And first I extend scalars to R1. So this is my omega. And then I extend scalars to R bar hat. OK. So this extension is in fact a refinement of Faltings extension. So the associated Higgs-Tate algebra is a refinement of Hyodo's ring. Then I can use this Higgs-Tate algebra to define the twisting functor that by the same formula as I said before here, using the weak P-adic completion of the Higgs-Tate algebra associated to this F. And if I start now from n theta, a Higgs R1 hat module with coefficients in omega, so it means it's a Higgs module here, I can first pull it back, twist it, and see what I can get. So first I pull it back, I call this n tilde theta tilde, then I can twist. And because what I explained before, I get not just a Higgs module, but I get a Higgs module with an action of delta. So I forgot about the Higgs field, and I just remember the action of delta. So in this way, I get a functor, which is this theta underline of n tilde theta tilde, from the category of Higgs R1 hat module with coefficients in omega in the category of R bar hat representations of delta. And I can just translate in this language the admissibility condition. So we say that n theta is solvable if n is projective over R1 hat 1 over p of finite type, and if the pullback is weakly twistable in the sense I said before. In fact, I told you before that if n theta is CL small, then the pullback will be weakly twistable. In this context, the two conditions are even equivalent. Then you have the following proposition. So the restriction of the functor V, let me go back, this functor, to admissible Higgs bundles, namely to the full subcategory of solvable Higgs R1 hat 1 over p bundles with coefficients in omega is in fact fully faithful. And we will say that an R bar hat 1 over p representation of delta is Dolbeau if it is in the essential image of this fully faithful functor. So V will induce an equivalence of categories between solvable Higgs bundles and Dolbeau representations of delta over R bar hat 1 over p. And we can even construct a quasi-inverse explicitly using the algebra C dagger. I give the formula here. And I will finish here by explaining now, so up to now we just use the module underlying the twisting functor. I will now say what we get from the Higgs field itself. So I start by a Dolbeau R bar hat 1 over p representation of delta. I take the associated Higgs bundle, I call it n theta. I pull it back to R bar hat, I call this n tilde theta tilde. Then because H and V are quasi-inverse, I know that M is isomorphic to V of n tilde, theta, which means it's equal to, which is equal to tau underline of n tilde theta tilde. But here I have a natural Higgs field, okay? So this is induced a Higgs field here. I call it theta M. So I get an isomorphism between M theta M and tau n tilde theta tilde. In this way, I obtain a functor from the category of Dolbeau R bar hat 1 over p representations of delta to the category of delta equivariant Higgs R bar hat 1 over p modules with coefficients in omega, namely M maps to M theta M. So it's defined equivalently by this formula. And up to now, all this construction depends on the lifting. I choose a lifting which is x tilde. But the proposition is that, in fact, theta m does not depend on the choice of x tilde. So this canonical Higgs field is, in fact, an analog of the p curvature of a module with an integrable connection in characteristic p. So I think I cannot say more on the globalization of this construction and, in particular, on the functoriality properties, because it became too technical. But if you are interested, you can read about them in these two books who are already available, and this book which should be soon available. Thank you.